first type of problem we're going to take a look at tonight, there's really just two types of things we're looking at. They're similar in nature. One, we're going to do it by hand. We're going to do scatter plots, identify lines of best fits. And then the second type of problem we're going to look at is we're going to do scatter plots, but we'll let the calculator plot it and then find an exact linear regression and exponential regression model for it. So what we're going to take a look at is the first examples. In most areas of the country, law enforcement has become a major concern. The number of law enforcement officers employed by the federal government and having the authority to carry firearms and make arrests is shown in the table for the selected years. Draw a scatter plot using these scales. So we're taking a look here. Oftentimes when you see things with dates, you are going to see them set some year equivalent to x equals 0. So we don't have to use such big numbers in our formulas and stuff like that. So in this case, this would be 1993, 1996, 98, 2000, and 2004. And so we'll have those types of things helping us out. And we want to build a scatter plot, estimate a line of best fit, and then we're going to choose 2 points on that line and help determine what the model of this function could be, and then we'll predict a couple numbers for 1995 and 2011. So the first thing we want to do when we're building our scatter plots today is take a look at identifying a label for the graph. And so in this case, we could just call it something like law enforcement. And so we'll look, that way you got some enforcement. Right, and then you want to identify what your x and y axis are. So we identified that the x was going to be our time in years, where 1990 was going to represent x equals 0. Yeah, so we kind of identify that. And then our y-axis is going to be the number of officers that we have in thousands. Okay, so now we've kind of got a rough labeling going. I want to find a scale that would be appropriate. So in this case, our numbers went from 1990 to 2005-ish. So we want to go like x from 0 to 15 or so. So I can just go up by ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we've got our scale there. I think the highest we had was like 90-something thousand, so we may want to go up by 5s or slightly more. Okay, so here we go 5, 10, 15, 20, 25. I don't know if this is going to actually fit because I shifted up my graph. So let's go by 10 is almost too much. Okay, so we'll go, let's just go up by 7. 7 will be a nice round number. Okay, so 7, 14, 21, 28, 35. 7, 14, 21, 28, 35 more. 7, 14, 21, 28, 35 more. So 105. Sweet, that worked. Okay. So our scale right now is by 7s. Kind of weird just because of the number I had there, but that's all right. So we'll plot these points. Again, the table we're looking at is here. So we've got 3 68s. Let me see if I can grab this really quick because I forgot to bring this over on my new chart we were using. Clipboard. Try to paste this in real quick and paste. Okay, there's our data. Okay, so we're going to plot these points. 3 68. 1, 2, 3. 70, so 68, somewhere in there. And then 674, 674, And then 8, 83, 6, 7, 8, 77. So that would be 84, 83 would be just below it. Okay. And then 10, 88. This would be 84, so 88 somewhere in the middle there. And lastly, 14, 93. 14 and 91, 92, 93. Okay, so we've got our points plotted. We want to find a line of best fit. Do we all remember how to find a line of best fit? Chris, how would you find a line of best fit? Good. Okay, seems just like it means, right? So we're going to take some line and we're going to make it, hopefully make a best fit. Now by best fit, we don't necessarily mean touches all of the points, but is relatively close to all the points. All of our rough estimates are going to be kind of close, maybe not exact, but it'll get us kind of close to these points, and we'll be able to go from there. So this could be an example of a line of best fit. You don't want it to touch all the points. You just want it to be where all these points are pretty close to that line. First thing we were asked is to do that, and then the second piece was, is there a positive or negative relationship between those? Or correlation might have been the other way you've heard it before. Does this have a positive or negative correlation, Dylan? Positive. How do we know it's positive? Has this positive slope to our line of best fit. So that basically is telling us as time increases, so do the number of officers. So it has this positive relationship up and up. Okay? So we have a positive correlation. The next piece it's going to ask us to do is grab 2 points on the line and identify what the equation of this model is to help us with future predictions. So we can go ahead and grab a couple points that look like they're pretty close to the lines, and we'll see where we're at. So this first point is roughly 1,63. And this line here is roughly 12, 77, 84, 91. Okay, so those are roughly accurate modeling there. And so I can find the slope of this line based on those points. And so our rise is going to be 28 over our run of 11. Okay. And so we can use that slope then to help us build the model. So the equation to this line is going to end up being y minus y1, which we call 63, equals our slope times our x minus x1. And then we can just simplify it into a y equals equation if we'd like. So y is going to equal 28 over 11x minus 28 11ths plus 63. So let's just get a rough decimal approximation of what that would be. So 28 over 11. So roughly minus 60.45. So this is, again, just a rough estimate. Depending on how you plotted your points, how you drew your line, you may have a slightly different slope, which would then give you a different y-intercept slightly as well. So all these will be hopefully close to each other, but not necessarily the exact same. Now you have the model. The question, it would be plus 60, thank you. Okay. Now we have a model, and so Ben, how would I go ahead and find coordinate points for 1995?
You go to 1995 on the x-coordinate line.
Okay, so that represented by 5 here, we're going to be roughly that point.
Yep.
What's a way for me to figure out what that value is? Based on the model we were able to come up with. Calculator, what am I calculating?
What the equation is.
And then what am I substituting for what?
Okay. Correct.
Okay, so we're saying that 1995 x equals 5. So if I want to know how many officers I have, we can substitute 5 in for x. So 28 times 5 divided by 11. And then we'll add this 60.45, and we'll see that this point is roughly 5, 73.2. Okay, so we roughly have 73,200 officers in 1995. Similar idea, I could go ahead and take a look at in 2011, which is when x is equal to. Jay, can we figure out where 2011 would be based on our graph and our starting point? If 1990 represents 0, what is x's value for the year 2011? Be 21. Excellent. So in the year 21, we're going to be somewhere up here that's off of our graph, but we can try to figure out what that is. Same situation. We'll plug in x equals 21. So 28 times our 21 divided by 11 plus our 60.45. We'll see that in 2011, or the year 21, roughly 113,900 officers would be employed. Okay. Questions on how to use a scatter plot and do that piece of it? Feeling fairly comfortable there? All right, so the second thing is we're going to use our calculator. So let's take a look at a slightly different example. Number 32 is going to talk about height of men and shoe sizes. Okay, so it's reasonable to think that the taller we are, typically the bigger our feet are. Thus, the bigger our shoes are going to be. Here is a table that is given for heights and shoe sizes. And we can take this information and try to plot this into the calculator and let the calculator do a majority of the work for us and give us a much more accurate interpretation of what's going on here. So, how many of us remember how to put stuff into our calculator and plot the stats? Okay, awesome. So those of us that have either never done that before or maybe rusty, let's take a look at that real quick. Pulling up your calculator. In order to input statistics, you want to go to stat. Stat is going to let you do a whole bunch of statistics stuff, and we can go edit our list, and we can actually enter some stuff. So if we take a look at our table of information given to us, we can take a look at that and then type this all into the calculator. So for our X list, we're going to put that into L1. If you want to follow along, please type in your X list in L1. L2 is going to be our Y list. So we can enter all that data. One of the things we want to make sure is once you've entered these amounts and these points, that at the end you have the same amount of X's as you do Y's. In order to make sure this thing plots correctly, you want to make sure that you have the same amount of X's as you have Y's. Otherwise, it's going to try to plot something that doesn't really exist. So we can have that piece plot, and then we can run some statistics on this. So let's say I just want to go take a look at this and actually have it show up. So second y equals, which is your stat plot. We'll go grab your stat plots. Let's grab the first one and turn it on. And then you can go to scatter plot, which is your first option. Underneath scatter plot, we'll hopefully be able to see this. So let's go click on graph, and it should show up. What happens if it doesn't show up? A window, right? We're looking in the wrong spot. Most of us will be in a 10 by 10 window, and it's not really showing up. And so I can go click on my window and determine, well, my X's go from the 60s to almost 80s. So my smallest X I could plug in is 60. My largest could be 80. That should fit everything inside of it. My scale can be pretty much whatever I want it to be. I'm going to choose 2, just because I don't like a whole bunch of tick marks. Okay, my y values go from like 8 to 14, so I'm going to choose 5 to 15. That should fit all my data points. Y scale again, you can choose whatever you want. Now we're going to graph, hopefully it shows up. Awesome. We got a bunch of points. So, looking at this picture, do you think we have a positive or negative relationship? Positive. So as we thought, as the taller we get, the bigger our feet tend to be. Do we think that's a linear relationship or non-linear? How many think that it's going to be a straight line? That looks pretty linear to us. How about a non-linear? Okay, awesome. So it looks like it's got a bit of a curve. It could be some sort of an exponential regression model. Let's see which one fits it best. So the calculator will do what normally would take us a ton of time, and we'll do it in a matter of seconds. So we can go back to our stat, and now we're going to calculate some ideas. So we're going to calculate a linear regression. So let's see how well a straight line fits it. So our fourth option is linear regression. When I execute this, it'll give me the form y equals mx plus b, and give me my slope and my y-intercept to a whole bunch of decimal places. Okay? Go ahead and you can jot those down, because now we can plug that into our y equals equation and actually see how well it fits. So in our y equals equation, we'll see that 0.469x minus 22.6. We're going to see how well that linear regression fits. Awesome, that looks pretty good. We got a straight line that goes through most of that data. But we're curious, well, it kind of looked like it was curved. So anytime you think that it might be a non-linear, you may want to check and see how well it fits in another format. So we can go back to stat. We can go back to calculate there. And then we want to go to the exponential regression model, which is your 10th item, or 0. 0 will pull that up for you. You can execute that one, and your exponential regression will come across in the form of a times b to the x, where a is that y-intercept, or our starting point, so 0.47. And then b, which is our growth factor. Make sure you grab that to at least probably 4 decimal places or so that it's fairly accurate, so 1.0448. We can take this equation and plug it in. I'm going to turn off the linear regression and turn on the exponential one, and we'll see how well that one fits. That one seems to get more of a curve, and it looks like more of those points are starting to get close to it. If we're still not convinced which one works better, you can always turn on both and then look and be like, maybe this one works better, maybe that one works better. So I'm going to go out on a limb and say this one looks like it might fit better with the exponential regression. So like we were saying, non-linear, I'm going to agree with you on that. So now we can go ahead and use that model. So I'm going to turn off the linear model. And we can use this model now underneath the table to help us. Okay, it asks us, when I'm 60 inches tall or 5 feet tall, how big are my shoes? Well, according to this model, we should predict that about a 6.5 or 6.5, size 6.5 is what you're going to wear. Okay, same idea. I can either scroll all the way down to 80, or I can go to table set and make my starting point 80. Go back to our table, and we'll see that if I'm 80 inches tall, my shoe should be about a 15 and a half. Okay? So this kind of helps us get those fits. Does that kind of cover most of the stuff we remember of how to set this up? So if you're having issues with your calculator, again, this will be posted online, so you can use that.